Welcome to our next lecture in the series on condensed matter theory. In this video I want to discuss the relation between the linear response in the time and the linear response in the frequency domain and show that indeed they are Fourier transforms of each other. In previous videos we showed you what the linear response in the frequency domain was, and we showed what the linear response in the time domain was, whereby we make an excitation which operator h1 either times sine omega t or some function in time, and we could derive that the response function when you make the excitation at t is equal to 0 is then given by the expectation value of the commutator of the operator with which you make the excitation and the operator with which you do your measurement in the time domain, or in the frequency domain you have the operator with which you do the measurements and then 1 over omega plus h0 minus the ground state energy minus h1 times h1 with a minus sign and then h1 and then the propagator 1 over h bar omega minus h0 operator with which you do the measurement and then psi 0. So what I want to show you is that indeed the susceptibility in the time domain is given by the susceptibility in the frequency domain, or the other way around, the susceptibility in the frequency domain is the Fourier transform of the susceptibility in the time domain. Now this derivation is very similar to the derivation that we did for Green's functions, and we start again with the Green's operator. Now it's a retarded operator because we're going to put the poles in the lower half plane, and we have both the advanced and the retarded part, the plus and minus part of our Green's operator. And we defined it as omega minus plus h0 plus minus e0 plus I0 plus. Now I can make a Fourier transform of this Green's operator to get the Green's operator in the time domain. And this is 1 over 2 pi integral minus infinite to infinite e to the minus I omega t gr plus minus omega the omega. Now in order to do this integral we can realize that our Green's function only has poles in the lower half complex plane. So if we look as a function of real and imaginary part of omega, then the poles are all sitting below the real axis, such if we integrate over the real axis and we can now close the contour in the upper half plane, then that integral is 0. So 1 over 2 pi, the contour integral enclosing the upper half plane of e to the minus I omega t, Green's function r plus minus omega d omega is equal to 0. That means that the integral over the real axis is minus the integral over the arc. So g r plus minus t, which is the integral over the real axis, is minus 1 over 2 pi integral over the arc e to the minus I omega t g r plus minus omega d omega. Now we're going to substitute. Omega is r0 cosine theta plus I sine theta, and with that we have g r plus minus of t is minus 1 over 2 pi the limit of r0 to infinite, integral 0 to pi, e to the minus I r0 cosine omega t e to the r0 sine, this is theta, sine theta t, g r plus minus of omega, which is a function of theta, r0 d theta. Now we have here an exponential in there, and when t is smaller than 0 and r goes to infinite, this exponential will suppress that function to 0, such that, or suppress that integral to 0. R plus minus, for the case that t is smaller than 0, is equal to 0. Now let's have a look what happens for the case when t is larger than 0. Now, for t larger than 0, the arc is going to give you some value. So this contour is not going to be very helpful, but we can make a contour in the lower half plane, and then we know that the integral over the arc is 0, such that the integral over the real axis is equal to the residues that we have of the poles. So this is 1 over 2 pi, the integral over the lower half plane, as the integral over the arc is 0, I can just add it, e to the minus I omega t, g r plus minus omega, the omega, and this is equal to minus 2 pi I, the 2 pi cancels with the 1 over 2 pi, times the residue that we have of e to the minus I omega t, 1 over omega, minus plus h0 plus minus e0 plus I0 plus. And here we have poles when omega is equal to plus minus h0 minus plus e0, such that we just find e to the power of where we have our poles. So g of r plus minus for t larger than 0 is minus I e to the minus I plus minus h0 minus plus e0 times t. Now we can combine this such that our full Green's operation plus minus our full Green's operator in the time domain is minus I theta t, because when it's smaller than 0, 0, bigger than 0, we have a value, e to the minus I plus minus h0 minus plus e0 t. With this we can calculate the Fourier transform of our susceptibility, and the susceptibility in the time domain should be the Fourier transform of the susceptibility in the frequency domain, which is 1 over 2 pi integral minus infinite to infinite psi 0 o, then the Green's operator plus omega h1 minus h1 Green's operator minus omega o phi 0 e to the minus I omega t d omega. And this is here the Fourier transform, where the wave function o and h do not depend on t or omega, so we can just Fourier transform our Green's operators. So this is psi 0 o g r plus of t h1 minus h1 g r minus of t o psi 0. We now can fill in what our Green's operators are in the time domain. minus I theta of t psi 0 O e to the minus I h0 minus e0 t h1 minus h1 e to the minus I minus h0 plus e0 t o psi 0. Next, e to the power I e0 is just a number, so that commutes with O, and then we can replace it by the Hamiltonian acting on the wave function, such that here we have the operator O in the interaction picture at time t. We have h1 without any time evolution, but of course the Hamiltonian interacting picture at time is equal to 0 is equal to the normal Hamiltonian, so that we can write this as I theta t psi 0, and then we have once O at time t in h minus h at time t is 0 OH time t, so this is the commutator of h1 at time t is equal to 0 and operator O at time t psi 0. Such that we are now full circle. We have shown in first by an example what the linear response of a two-level system is, then derived what the susceptibility is in the frequency for a general system, derived what the susceptibility is in the time domain for a general system, and now shown that indeed they are the Fourier transforms of each other. So with this we have a full handle on the response functions of our system, both in the time and the frequency domain. I find it always very nice to talk in the time domain when I explain physics, because there you really talk about, well, you propagate, you have an interaction and you propagate again. But once we have to do real calculations, then doing the calculations in the frequency domain actually helps a lot with numerical stability, because, well, when you excite something, it just starts to oscillate at its eigenfrequency, and that's of course only a single frequency, or if you have 2 or 3 frequencies, only a few frequencies, whereas in the time domain very complicated behavior can happen. In the end it comes down to the product of a susceptibility times a force function is easier than a convolution, already in a classical sense. And in quantum mechanics, where time evolution of states can grow exponentially in computation cost with time, being able to go to the frequency domain really helps a lot and can make calculations that wouldn't be tractable otherwise tractable. Thank you very much for your attention. Hope you enjoyed these derivations. I realized there's a little bit of math in there. Stay healthy. We see each other later.